I'm Ryosuke Akashi from University of Tokyo. So first, I'd like to thank to the organizers for organizing this great conference under the difficult situations and giving me opportunity to talk about our study. Yeah. So today I'd like to talk about our development of exchange correlation potentials in density functional theory using a neural network technology. And this is a main contributor of our project, Mr. Ryo Nagai. Okay, so although in this conference many talks concerns the application part of the DFT calculations, but our target is about the development of DFT itself. So for that, I'd like to start from the fundamental theory of the electronic structure. So the electronic structure is ultimately calculated by solving the many particle Schrödinger equation, as you know. So here the Hamiltonian contains the electronic interaction effects, and psi GS represents the ground state wave function. But the exact solution of this Schrödinger equation is numerically too demanding and almost impossible in many cases. But instead, the density functional theory assures us to allows us to recast the problem to corresponding non-interacting problem. That is the Kohn-Sham equation. The Kohn-Sham equation has a non-interacting equation form and contains the electron kinetic term, electronic ionic potential term, and Hartree potential term, and VXC, exchange correlation potential term. And the density functional theory assures us that by solving this Kohn-Sham equation instead, we can obtain exact ground state charge density. But there is a requirement for that. So the exact ground state electron density can be obtained if appropriate functional form of VXC is used. And actually, still the exact functional form of VXC is elusive. So therefore, there have been history of developments of exchange correlation potential VXC for good calculations. And maybe we are now coming to a historical point where machine learning assisted exchange correlation potential comes to the accuracy of the existing functionals designed by human intuition. So this is a figure of our test calculation comparing the machine learning designed VXC and the standard existing VXCs. So different colors represent the different levels of approximations for VXC, and open and closed symbol represent our machine learning assisted designed VXC and the standard VXC respectively. And x-axis represents electron density error, and y-axis represents atomization energy error compared with more accurate CCSD calculation. So as we go left down, the calculation accuracy becomes better for small molecules. So this figure indicates that the machine learning VXC is now already competing with the standard existing functionals. And in this talk, I'd like to introduce the background. I'd like to introduce this result with background theory for it. So let me start from the fundamental theory. So exchange correlation potential VXC is defined as a functional derivative of a quantity EXC, exchange correlation energy, with respect to the charge density value at point R. And the quantity exchange correlation energy is defined as follows. So here, the left-hand side represents the ground state total energy for a given charge density distribution N. And sorry. And the total energy is decomposed into 4 contributions. First one is the electron kinetic energy. And the second one is ionic potential energy. And third, electron Hartree energy. And the exchange coefficient energy is defined as the residual part of those 3. So at least this definition is concrete, and this definition gives us the procedure to define or calculate, in principle, Vxc as a functional of charge density distribution n. But this procedure is not practical because it already contains the step of solving the original Schrödinger equation here. So so this procedure is not practical as a definition of Vxc as a functional of n. Instead, we can also employ another definition for Vxc. So Kohn-Sham density function theory assures us that the Kohn-Sham equation reproduces accurately reproduces exactly the ground state charge density by solving that. So inversely, with given ground state, conversely, with given ground state n, we can optimize Vxc so that n is reproduced through the Kohn-Sham equation, and thus we can obtain Vxc as a function of n as by solving this inverse problem. But this inverse definition of Vxc as a function of n is still not so practical because this inverse problem is really difficult to solve. Anyway, Vxc is finally functional of charge density and charge density distribution n, and here the machine learning comes in. So the supervised machine learning is a procedure to formulate a function in a mathematical way. I mean mathematical, programmable or calculable language. And it refers to a massive amount of input and output pairs for reference. And here I mean by word function, any vector to vector mapping. So x vector as input, and through the function f, y output vector y. And here we recall that the functional n to Vxc can also be represented as the vector to vector mapping. So it can be finally represented as, for example, n as vector representing the charge density value at R1, R2 point, etc., to the Vxc distribution at R point R1, point R2, blah blah blah. So we find that we can find that n to Vxc relation is also a vector to vector mapping. So here one can conceive that machine learning can implement the n to Vxc relation as a vector to vector mapping. And for this goal, we employ neural network. So a neural network is, the nonlinear mapping from vector to vector through repetition of linear and nonlinear transformations, represented by this kind of graph. And for example, fully connected neural network formula operates to the input vector n, the linear transformation, and later nonlinear transformation to the vector components. That is called nonlinear activation function f, and repeat this. And actually, this model form is extremely flexible. That is represented by the universal approximation theorem that states any well-behaved vector-to-vector functions can be well reproduced with arbitrary accuracy. So here we are coming to an idea that although the M to VXC relation is difficult to execute, still, if we have a few examples, maybe we can mimic the exact M to VXC relation by numerical method, numerical neural network. Yeah, and here, finally, we come to a usage of neural network for DFT theory. So we train the neural network with some representative systems and apply it to more general systems. So actually, this is just a generalization of our practice for example, local density approximation. So in this case, we train the function with uniform electron gas and apply to non-uniform systems. So actually, the machine learning implementation of DFT functionals and application of it is just a generalization of our activity, standard activity done with local density approximation or general gradient approximation, etc. Okay, and here I am showing two our examples of demonstrations. One is fully non-local implementation of VXC for simple model, and second, a semi-local implementation for small molecules. Okay, let's start from very simple model. So here we show our results for a simple model, two spinless fermions in one dimension. So this system is represented by the Hamiltonian having this form. So it includes the kinetic term and the electronic potential term and the electron-electron interaction term. And here, the external potential is modeled as attractive Gaussian, parameterized by A and B here. And the Kohn-Sham theory assures that there's a corresponding Kohn-Sham non-interacting equation having this kind of form. And here, V Hartree exchange potential comes in. And Kohn-Sham theory assures that this equation reproduces the exact ground state charge density as same as the Schrödinger equation. And here we demonstrate the specific form of VHXC using the neural network. So for this, we first solve the Schrödinger equation exactly for given parameters A and B in order to get physical charge density distribution N. And next, we solve the Kohn-Sham equation with varying, optimizing VHXC so that the given charge density N is reproduced. So with this procedure, we can get the training input-output data. Input, in this case, means charge density N, and output means VHXC distribution. And after collecting training data, we next implement a neural network. So in this case, we discretize the real space grid, discretize the real space by a grid 100 grid points to represent the charge density and the VHXC distribution. And the number of hidden layers of neural network was set to 2. And the number of intermediate nodes, number of nodes per layer was fixed to 300. And as a nonlinear activation function, we employ the rectified linear unit. And we define error function to be minimized by the difference between the VHXC distribution calculated by neural network and the VHXC calculated from the original inversion problem. And we optimize the neural network parameters to minimize this value. And after training, let's go to the result demonstration. So for that, we solve the constant equation for given untrained potential parameters A and B using the trained neural network VHXC, and evaluate the errors compared with the exact diagonalization result. And here we are showing two kinds of errors defined by the charge density difference and the energy difference. So let's go to the result. So the left and right panel shows the charge density and energy errors, and X and Y axis represents the potential parameters A and B, and the yellow frames represents the training range where training was done. And here, this color figure shows us that constant neural network VHXC retain its accuracy even if we go out from the training range, as long as we are not going to be going beyond the boundary here. So what's this boundary? So we are finding that the accuracy of the calculation goes down rapidly by going beyond this boundary. So actually, this boundary is determined by the physical property of the model. So beyond this boundary, the ground state is a two-particle. In the ground state, the two particles are bound, but below this boundary, only one of the two particles is bound. So there are crucial difference between at this boundary. So the result is now simple to understand. So in this case, we train the neural network potential using only one particle bound state. So it cannot represent the two particle bound state efficiently. And actually, inverse is correct. So if we train only two particle bound state, it retains accuracy for two particle bound solutions, but not for one particle bound solution. So is there a way to retain the accuracy for the whole parameter regions? Actually, yes. So by setting the training range across the boundary, we can retain the accuracy for the whole region like this. So this result is for simple model, but give us important instruction. So if we train the neural network exchange correlation potential with enough diverse characters of ground states, it can retain accuracy for a wide parameter region. So with this result in mind, next we are going to the second example, semi-local implementation for small molecules. So we are recalling that generally the VXC as a functional of charge density n can be represented as the vector-to-vector mapping. In this case, for this, we first express the EXC as a function of this form and introduce exchange correlation energy density like this, which depends on local descriptor vector G n over R. And here, local descriptor vector G can include, for example, charge density at a point nr and spin density at point R. So with this definition, this approximation corresponds to so-called LSDA. And if we extend the vector by including a gradient, this corresponds to GGA. And by including a kinetic energy density, it corresponds to meta GGA, blah, blah, blah. We can extend the local descriptor vector. And in this case, we implement the mapping from local descriptor vector to local exchange correlation energy density with a neural network. And VXC is defined as the functional derivative of EXC and calculated like this. And here, this involves the derivative of epsilon xc, but it can be efficiently calculated with the backpropagation technique implemented in standard neural network packages. And here we are showing the our demonstration, where we train the neural network functional with reference data from accurate wave function theory, in this case CCSD, and apply the trained neural network to Kohn-Sham equation and calculate properties of unreferenced systems. And for training, remarkably, we define error function referring to only 3 molecules: H2O, NH3, and NO. And we define the error function to be minimized by the charge density error compared with CCSD calculations, and the atomization energy error compared with G2 dataset, the G2 dataset set. And here we respect, we chose these 3 molecules in order to respect the diversity of descriptor vector G. So it should be low symmetry. It should contain low symmetry systems and the electrically polarized system. And also it's necessary to include spin polarized system in order to implement the dependence on the spin density. And here we optimize the neural network by this kind of procedure. So we randomly change the neural network parameters slightly and solve the DFT calculation using the functional and evaluate the cost function. And we decide acceptance or rejection of the parameter change based by the metropolis type update. So actually, we have to admit at this point, this optimization procedure is not does not refer to the derivative of the error function. So it was not so efficient. And recently, more efficient method has been hopefully implemented by other groups. But anyway, in this case, we are successful in optimizing the neural network parameters this way. Okay, so maybe one would wonder if only 3 molecules may not be enough for training. But actually, yes. So we find that the only even in one system we have the distribution of local descriptor. So various kinds of GR values can be obtained with single molecules. I mean, so any mesh point can carry different values of GR. So with only one molecule, only single molecule provides us enough information for training the neural network. So especially we solve the Kohn-Sham equation to fit the whole density distribution is well reproduced. So with only the single molecule can be enough for training a massive number of neural network parameters. That's the point. And this is the result. So this is the average error of 147 untrained molecules. And this is our performance of machine learning designed neural network VHXC. So now we come to this accuracy. And also maybe time is going up. So let me go quick. So more remarkably, we would point out that the machine learning neural network scheme gives us efficient method to extend systematically the VHXC functional. So here, as a red point, we also tested our implementation of non-local descriptor. And remarkably, its accuracy is going beyond the hybrid functionals. And here we extended the local descriptor by including one variable, large R. It is defined as the integral of charge densities at certain reference point around a certain reference point by some weight. So this variable can include non-local effect. And remarkably, this gives us more accuracy than hybrid functionals. And importantly, this kind of extension is at least straightforward, even with the neural network scheme. Simply increase the variable and optimize the neural network. Systematic. Okay, let me summarize my talk. The fundamental value exchange correlation potential is finally can be represented by vector-to-vector mapping from charge density to potential distribution. So it can be implemented by machine learning scheme. And with this scheme, we are now coming to accuracy comparable to the standard functionals. Thank you for your attention.